All right, good morning, everyone. Sorry, we're starting a little bit late, but we'll get going here. So last class period, we had our midterm, and I can't hear myself. And I graded everyone's midterm already. I think you should be able to see your grades. If someone can confirm, I published them. I don't know if you can see them, hopefully. Can you see it? Yes? Okay. Yeah, so well, once you check, let me know if you can see it, and also if you can see which ones you missed and how many points you got, like if you got no points in the question or if you got partial points. Nope. GOT cannot see, like not even the grade?
No.
Okay, I'll look into that after class today, but you can see, Benita? So you can see both the grade, the overall grade that you got, and also which questions you missed? No, cannot see the questions? Oh, nothing at all. Benita, could you repeat, please, which steps you took to see the grade?
And then from there, I go for submission.
Submission. Okay, so tools, quizzes, midterm, submission. She got, I cannot see anything, so Austin said. So I think on my side, even if I show you, it's gonna look different. So I don't know how much of help I can be. Let's see. Okay, so Austin found it. Let me see, let me log in into mine here.
Yes, if you will click on attempt, then you can see your.
On attempt?
Yeah.
Okay.
Yeah.
Can you all see like, so your overall grade and also how much, like which questions you got right and wrong?
No, only
No.
overall grade.
Only overall, okay. So I'll look into that and see if I can make it available to you, because I want to need to see what you missed. Yeah, so I'll work on that after class today, and I'll email you with more information about that. So I guess now we can see your grade. I mean, I think the overall average was 80%. I think the maximum was 98, and the minimum was 36, I think. So yeah, we'll talk more about that next class period. Okay, another thing before we get started, I know that some of you emailed me with questions and perhaps asking for extension on your submission of the project. I have not been able to get to your emails yet, so if you have emailed me, I will get back to you today. And I'm noticing that a few groups asked for an extension, and to be fair with everyone, I want to give that extension to everyone. So I'm going to extend the deadline to next Thursday. So instead of being this Thursday, you have up until next Thursday, but that's going to be a hard deadline. Like I will not extend after that. So make sure you start working. If you have questions, I want to help you. Reach out to me, but not on Wednesday afternoon. That's not going to work. So reach out early and I will definitely help you. I know some of you have already reached out and I'm glad to help you. But just really try to do that with, some days in advance, because I know you're all probably starting few work, going to be busy. And my schedules, depending on the day, look very hectic and I don't have many open slots depending on the day. So if you do want some help, let's plan accordingly. And I do want to help you. My goal is for you to complete the project successfully, so you have some idea of how to apply the concepts we learned to your projects. That's my goal. And so I do want you to do this, the best way possible, the best way that you can, based on what you learn on the class. All right, I guess any questions about maybe your overall grade? I mean, if you have a question specifically about your overall grade, maybe wait until you can see what questions you missed, and that's going to help you better understand how you got the grade you got. but maybe any questions about the project, like overall questions, not specific questions, I guess. Sorry, can you? Yeah, I mean, if you have any overall questions about that. Okay,
Like, I got AIC just that is negative, and then I look for a reference that which value should choose. I got like some say that the highest value, absolute highest value, if negative and absolute highest value should we choose for the model fit, but some say that we should choose the value which is near to the zero. And that is like confusion, so I'm confused with which value I should do.
okay, let me repeat that for those online. So Benita is asking that for her project, she is doing a model comparison and she got a negative AIC, BIC values. What should she do? So to tell the truth, I never came across a recommendation of looking at the ones that you mentioned. I would still select the lowest value. Of course, if you think of a lowest on a negative scale, it's gonna be the absolute largest, but it's on the negative scale, right? So it would still be the smallest or the lowest number in that sense. And really, AIC and BIC, they are relative measures, right? So it's okay if they're negative, there's nothing wrong with that. It's more about being able to relatively compare models that have a similar structure, is just changing, you know, some parts of the model, but the same data, especially if those models are not nested, which ours are not, depending on, I mean, what we did in class, some of them you may consider nested, but anyway, I don't want to add more confusion there. I guess what I'm trying to say is keep using AIC, BIC, the lowest is the best fit, still even though on a negative scale. Well, it would be the lowest on a negative scale, right? So if you take the negative value of the absolute value of that, it would be the highest then. But yeah, I know it's it's confusing. So let's say. Interesting.
Like something that multiply with -2 and get the value, which get like highest value. And something near to the zero and there is two, like,
Yeah.
even in the online, we do a lot and can.
Yeah. So let's think about it. If you have like a -10 and a -20, which is the smallest? -20, right? So you choose -20. So that, yeah, I mean, we can stick with that. And I mean, that is what I learned and the references I use that. If you find like, really, you know, this is science. As long as you can back up your decision with a reference, I'm not gonna discount points, right? So I mean, there's, you know, I'm teaching you things the way that I learn and that I do myself. But, you know, nothing is absolute. So if you decide to take a decision and that is different from what we've been talking about, and as long as you can back up, just like in a paper, right? Like you have to back up your decisions with literature. As long as you can do that, I'm fine with it. But yeah, absolutely. Awesome. All right, any other questions about the project? Yes, Chris.
When I was running EM means and CLD to like extract the pairwise comparisons, I was trying to figure out, I know in the CLD function, you can use different options for, I think it's method. I think in class we've used none, but I was trying to do it 2 keys. So I was trying to figure out what was like the default pairwise comparison being done, because I added 2 key. I kept getting a response that said change to SIDAC. And I looked into SIDAC and just got more confused. So
SIDAC, what does that mean?
yeah, it's another means of pairwise comparison, but I think
SIDAC.
yeah.
Yeah, so you would change that on the adjust argument, right? So it's not, I mean, I don't know, maybe if you're using a method argument, I don't think that's it. You want to change the adjust argument.
Yeah, that's the one. Sorry.
Yeah, and there, if you just write 2 keys, it should take that as an argument. And I never got exactly what you're saying as far as, I don't even know what SIDAC means. But we can look into it. Like what I would, like if I ran into that issue myself, I would explore the documentation of the function and try to understand if they explain there, like what is going on. And because if they have situations like that, they will most likely like try to explain the documentation. Did you look for that
I
or?
looked into it a little bit. It wasn't immediately clear. I'll look into it again. When we select none for the adjust, what pairwise comparison is being done?
So that's, so is no adjustment, no actual adjustments being done, right? So that's why it's called none. But if you look on the literature, that's what would be considered the Fisher's least square difference, which is basically the only adjustment, because really, if you think of it, you could do pairwise comparisons without ever looking in an ANOVA table. You can run a model and go straight to pairwise comparison. There's nothing stopping you there. So the fact that we do check the ANOVA table with the sources and the p-values first to decide how we're gonna extract means, that's like an adjustment in itself, not necessarily an actual adjustment, but it's just a check that you're making sure you're only extracting means for things that were significant on the ANOVA. And that's what Fisher's LSD means, if you read, when you read that on papers. Yeah. Yes.
I was just trying to run a model, so you remember, you have different depths,
Mhm.
sampling. And one trying to fit that in the model. I was confused, like, how am I going to incorporate that depth in the model? Do you have some insights on like what can be done?
So you're trying to run that as repeated measure?
There were measures for location, EC and all the values that I have. But I'm pretty sure that the values of whatever I'm trying to look at, actually it's carbon. So it
Mhm.
increases with depth normally.
Yeah.
In general sense, so I also wanted to make sure that I incorporate depth into the model.
Yeah. So that's a really great example. And so what Anis is saying is that he has repeated measure in space because he has the geo coordinates of places where he took the samples. But so you actually have two repeated measures, like you have an X, Y, and Z, right? So you have repeated measures in 3 dimensions, not only 2. Because you have soil depth, right? And so depth you cannot randomize, right? You cannot say that you're taking the 15 or 30 before you take the 0 to 15, right? So it's no randomizable. And to tell the truth, I never ran a 3D repeated measure before. So from experience, I would not be able to give you an answer right off the bat. So I would have to read more and learn it. And if we just take one step back, if you include depth as part of your model, and this is, I guess, an interesting conversation overall for repeated measures. So repeated measure is important when you do want to be able to compare across those levels. So let's say in your case, if you do want to compare depth, the first depth with the second depth, and that comparison is important to you, then you need repeated measures for that. However, sometimes, at least in my case, a lot of times I don't really care if like the 0.15 has more or less nitrogen than a 15 to 30. I just want to compare 0.15 across treatments and then 0 to 30 across treatments, right? I don't care about this comparison, just this comparison. If that is your case, then you can simplify things by running a model for each one of the depths, which even though if you were to combine everything in one analysis, that would be repeated measure, but if you compare them in separate models, it's not repeated measure anymore because you don't have that time component as part of the model. You have the time component as part of like being one model for each depth in that case. Does that make sense?
We'll
Yeah.
discuss more about it after the class.
Yeah, but it's, yeah. Yeah, absolutely. But it's a great point because, you know, a lot of, so I did some work in greenhouse gas emissions, which we measure the same plot over time within the season. And that is a conversation that you see in the literature is if your goal is to be able to compare across dates, then you should have one overall model where date isn't as part of the model, and then you treat that as repeated measure and do all the exercise we did. But if you really don't care about if today was higher or lower than yesterday or tomorrow, you just care about within the day, the treatments, how they compare, then you can run a model for each one of the dates, and then that's not repeated measure, right? So yeah. In your case, I think it will come back to your hypothesis and your objectives. If you want to compare across depths, then you would have to run, like properly, you have to run the 3D repeated measures, which starts getting very complicated. But if that is not a question of interest, I would propose that you just do each depth as their own model and do not have depth as a factoring model. All right, any other questions about projects, overall questions? Yeah.
May I go back to Chris's question?
Sure.
So, when he was saying that for some reason, when you specify in the adjust 2 key,
Mhm.
its output, the output that it gives is two keys only appropriate for one set of pairwise comparisons. So that's why it
One
changes
set.
to see that core side of it.
Okay, is
But
any,
I don't know what exactly that means.
yeah,
Two keys only appropriate for one set. of pairwise comparisons.
let's take a look at that, because it may be something, maybe it's something related to how you're asking for the means and how the model was specified. That may be, I mean, I never got that on my side, so I really don't know from experience how to solve it.
Uh-huh.
Is anyone else getting that issue on e-means?
But it's only when you change that null
To adjust. Interesting. Well, I'll help you guys to try to troubleshoot that. I really don't know the answer, but we can look into that. And since it seems like no one else is having that issue, then maybe we can do that more on a one-on-one or one-on-two basis. And go through that. All right. Any other questions about the project? Overall questions? Yes.
Is there a way to save, like when we run, random, for random effects, like, if we choose one parameter and we run random effects for that? So
Mhm.
can we save that table if we want to?
Which table?
Like the table, so for my data, I have got a table for my genotypes that shows random effects. So
Mhm.
is there a way to save that? Because with ggSave, it only saves ggplot.
Yes, okay, so I don't know. Yeah, I don't know if in this class we did much of that. In my other class, we do export a lot of layers in between. So what I would do is anytime you have an output that's like a table format, if it's not a data frame yet, I would just pipe that into a as data frame function. And if most of the time that works, there's some objects that are not data frames that they would not like to become data frames. But I will try that first, and if you can turn that into a data frame, then you can just pipe again and do a write CSV or maybe a write Excel and export that to file that way. Yep. All right, any other questions before we resume class or the exercise? Okay, I don't hear anything, so let's resume where we stopped, I guess, a week ago. So I just launched here. So we want to finalize this exercise today, the multivariate, where we looked into multicollinearity issues last time. Right now, my environment is empty. Maybe yours is as well. Just want to quickly look in our chunks. I think we can just run all above, and that's not gonna take a lot of time, I don't think. Yeah, so maybe if you want to come, so if you go on your outline and you don't have your environment is empty like mine, you want to come to PCA, which is where we were about to start. And then you can just click on this run all above. That's just going to make sure that all the chunks above are run, and then you have those objects in your library, or sorry, in your environment. This is something that has been happening to me here. I think is partially a bug, I guess. If you're also seeing this where you're trying to scroll and there's this annoying output that doesn't go away. This is the output of one of the chunks, I think on the PMAT chunk. Let's see here. So if that is like in your way, you can just close the output of that chunk by clicking. So if I just print it again, if you just click the X button, you close the output of that chunk. I'm just going to inhibit this from printing again, because for some reason, I think it's such a long print that is just interfering with the script itself as far as being in front of it. So if you're also having that issue, that's how I would fix it. Okay, so we stopped at talking about multicollinearity, right? So we ran a few models where one of them had no multicollinear explanatory variables. The other one had two multicollinear variables, and we noticed that when we had the multicollinear variables, there are two things that happened. This was a question on the exam. So first is the direction and magnitude of the estimates of the model may change from a model that's collinear and one that is non-collinear. And also your standard errors of that estimate get inflated. So you have more uncertainty when you're trying to assess that effect. And then we check multicollinearity using the VIF function, the variance inflation factor. And we have this rule of thumb here that's if it's around 1, there is no multicollinearity in the model. If it's between 1 and 5, there is moderate multicollinearity. And when if it's greater than 5, then it's severe multicollinearity. We checked that for the model that was non-multicollinear. The VIF values were 1 for both of our axes in the formula. The VIF for the model that was multicollinear was 64 for those two multicollinear variables. So this is a problem that we have to think about and find ways to address it. So I have here some topics that I want to discuss with you about it, right? So if we do get in this situation where we know we have multicollinear variables, which again, the way that we checked the potential, even before we started modeling, the way that we check for a potentially multicollinear variables was by running that correlation matrix, right? And looking at those values. We saw that some of these variables here had a correlation coefficient of like either 1 or -1, which means very strong R. So this is correlation coefficient is R, so very strong correlation there. Meaning that if we include those pairs of variables in the model will be multicollinear. So then how do we address that? So there's a few options that we have to address it. So the first one would be dimensionality reduction. This is something that you're probably going to hear if you haven't heard yet. You're going to hear this more as you work more in data science because this is a big topic because of multicollinearity. And if you think about it, there are a couple ways that we can do it, where one is by hand. What I mean by that is basically you as the expert, you would only select into a model the variables that you know from the literature, from your experience, that do impact your outcome, right? So it could be from your knowledge, it could be from the literature. It could also be based on the correlation that we already checked for those variables. So let's say we had a whole bunch of pairs of variables that had a very high correlation. We can go back to that and think, okay, of these variables, I really want to keep one of these two. So I don't want to include both of them in my data set. I will remove one of the pair. So you can do that as well. Check for those, only allow to remain in the model the ones you think make more sense. If you're really like, there's a lot of literature in machine learning, especially that do highly recommend that we are very explicit and science-based when creating these variables and entering them in models. So in other words, what we just did with our feature engineering was create all these potential variables from January to December for all these weather variables, and we just have them in the data frame. Even though we have some hypotheses of how those weather variables can impact cotton fiber length or cotton fiber strength. Yeah, that was the variable. Probably, like something like temperature in January is probably not impacting because cotton is not even planted until at least May, at least in Georgia. So no, there's some of that data that may have nothing to do with what we're doing. It's just a result of us just doing a lot of feature engineering from weather data. So we can use that to select variables just by hand, I guess. The other way would be using math, using some algorithms. So one that we're going to see here is going to be principal component analysis. There is a suite of different algorithms to do dimensionality reduction. I want to show you one of them and go in more detail on that. But I do want to let you know that's not the only one, but probably the one that you see most of the time for this purpose. Another way is actually, so not doing dimensionality reduction necessarily, but using an algorithm, a machine learning algorithm that handles multicollinearity. So that can happen in a couple of different ways. One of them would be if an algorithm already performs variable selection for you. You may be only selecting variables that have a higher predictive power and not including all those variables in the model. So one example of this would be lasso, so least square shrinkage. What is the O? optimization perhaps, but it's one of the things we're gonna look and learn later in this course. Another one, so if you think of it, there are decision tree, we're gonna learn one algorithm for decision tree that basically does variable selection in a way that we're gonna, when we get to that, we're gonna understand better, but decision trees can also do variable selection for us and not be susceptible to multicollinearity. Another way is using multivariate algorithms that use ensembling of multiple bivariates. So one example of this would be a random forest that works by ensembling, stacking and assembling different trees in the forest to give you a prediction. So there are some issues with random forest and multicollinearity that we're going to talk about when we get there. But for the most part, random forest would be less susceptible to multicollinearity than some of other linear models that you can run into. All right, so I guess on this text here, so what we're gonna get to here is that some of these models, they will be, I guess not talking about multicollinearity necessarily, but just how to build some of these models that we're gonna do today with principal component analysis and k-means for clustering. Some of these models, they if you give different variables that have different magnitudes. So if you think about it, I guess in this example here I have from our data, so the mean temperature in January ranging from -10 to 10. So this is the range of values the model will be seeing. Comparing that with mean day length in July, that varies from 48,000 to 51,000. So these variables have different magnitudes to begin with. And depending on the model will not be able to really account for this and will give more weight to variables that have a higher magnitude in value, even though they may not be the most important for the model. So for us to handle that and take care of that, we may need to normalize our variables so they have a mean of 0 and the standard deviation around 0. So we don't allow the magnitude of the variable to impact how important a given algorithm understands that variable is. So because of that, and especially in our case here, we do have that issue where our variables have different units that are in different magnitudes. But we'll need to normalize by centering and scaling before we start some of these analyses. And some of these analysis, so we're going to do principal component analysis, PCA, which is a dimensionality reduction, and then we're going to do k-means, which is a clustering algorithm. Some of these analyses may already do normalization for you, like PCA does that for you, others don't. So k-means, for example, does not standard or normalize the variables for you. So we need to be aware of this when we are working with data and we're feeding into these different algorithms. Now, both in the case of principal component analysis and k-means, as we're going to start talking more about them individually, but overall, they only accept numerical variables. There is a trick, I guess, to get categorical variables into these algorithms, but we're not going to see that here. We're just going to only keep our numerical variables to get into these models. So I do want to do a light wrangling here to just keep that. So if you come here on the next chunk, let's just do that here. So the data set we have right now is called weather. I just want to print that below so you see it. We have again our 698 site years and 75 columns, where most of these columns are numerical. The only one that is not, I think, is site. And so we don't really need to have site there. So let's just do a select, one of the dplyr, : select. And I want to, it's going to be easier for us to remove the variables we don't want in this model than the ones that we want. So I actually want to remove, starting on year, going through strength. So we can either do -year : strength, text. That did not work. Maybe we need a C function here. Let's try that. That did not work either.
TH on the string.
Oh, okay. Thanks. So I misspelled here. All right. Thanks, everyone. Okay, so did it work without the C? I was wondering, since no, it did not work properly. So we need a C there. Just to concatenate. Yes, thanks, Sikar. So Sikar is showing a different option here that you just do minus ear, colon, minus strength, and that gets the same result as using the C function here. All right, so we just kept here our 72 variables, weather summarized variables for all the data, all the site years. And now we're gonna get into principal component analysis. So again, principal component analysis is a dimensionality reduction approach that only accommodates numerical variables. So by dimensionality reduction, what we mean by that is, so right now we have 72 variables, and we know there are some highly correlated variables in the set of variables. Principal component analysis is going to help us to identify features within our current variables that represent the most variability within this data set, but are not our original variables themselves. They're called principal components. So really is going to look for linear relationships among all these predictor variables that we have, and representing that in a lower number of uncorrelated dimensions. I think this is a very important concept here. So let's see, I have some text here. Let me not make sure I'm not getting ahead of myself. Okay, I guess I'm going to follow this and comment as I comment in here, so I don't get too confused on my head as well. So for principal component analysis, or really any dimensionality reduction analysis to work well, you do have to have correlated variables to feed into that algorithm. The reason for that is because PCA is going to look for those variables that are highly correlated and create linear features out of them that are going to be our principal components. So normally, let's say if we have here 72 predictor variables that were given PCA, it may come back to us and say that out of those 72, you're going to need, so it's going to calculate one principal component for as the name number of principal components as you have features. So it's going to give you, if we give it 72 features, it's going to give us back 72 principal components, which are going to be each one, they're going to be a linear relationship of all your original variables, all the original predictors, but differently in a way that they're going to be, or first off, going to be orthogonal. So your PC1 to all the way to 72 are all going to be independent. And they're also going to be, PC1 is going to explain the most variability in the data set. PC72 is going to be the least, in a way that maybe you can select 5 or 6 PCs out of all the 72 and explain maybe 70% of the variability on your data set, which is pretty good. So you're basically going from 72 variables to, let's say, 5 or 6 principal components that are allowing you to explain about 70% of variability on your data set. Plus, the principal components are orthogonal. They are independent. They are not multicollinear. So it's both of these features of decreasing dimension and also in a way that they are orthogonal, independent. They will not be multicollinear if you run an analysis with the PCs instead of the variables themselves. We're going to see this at play, and I hope it will become more clear as we play with it. So I guess just some points here about PCA. So it is, again, a dimensionality reduction algorithm. It is unsupervised. So what that means is that we're not given a Y variable. We're just given all these X variables. If we wanted, we could have given strength as an X variable in the model as well. We just give all these variables and say, create principal components out of these variables. I decided not to include strength there, but we could have if we wanted. But the main goal, the main idea is that it does not have a Y variable, right? It only has X's, so it is unsupervised analysis. Which also, in other words, it means that it only takes predictors. It does not take a predicted variable. And those predictors need to be numerical. I guess I was just telling you about some of these properties here that, one thing that perhaps can be confusing in PCA is that principal component analysis, and I just want to rephrase this again, is gonna calculate, give back to you the same number of PCs as you have variables that you gave the model. So if we give 72 variables, it's gonna give you back 72 principal components. The overall variance that each one of these principal components explains is gonna be the greatest for PC1 and is going to decrease after that. So the higher is the PC number, the less variance that PC is going to explain that was present in your original variables. That's a mathematical characteristic of PCA. And again, one of the really great features is that the PCs are all orthogonal. So even if all of your variables are correlated to some extent, your principal components are gonna all be independent. They're all gonna be orthogonal. They're not gonna be multicollinear in a linear model. And really, again, the goal of PCA is so you can use this, and instead of feeding into, let's say, a random forest or any other machine learning model, instead of feeding all of your features, all of your weather variables, you may feed into it the principal components based on those variables, which are gonna be, again, non-multicollinear, gonna help you with that issue. So I have here a GIF that I wanna show you of what is happening with PCA. So this is gonna start again, this GIF, and I'll start talking when it starts again. But basically, the goal here is we have, in this case, two variables, so a two-dimensional principal component analysis, which is really, I guess, not, we have 72 dimensions if you think about it. This is just a very simplified example with 2 dimensions, X and Y. So step 1 standardizes the data where it centers both the X and Y variable at 0. That's what it did first. Let me wait for it to come back to the first step, so we'll keep talking at that point. All right, so it standardized the data, so it is centered on 0. Then it calculates a covariance matrix. So this is something that it does by itself behind the scenes. Then calculates the eigenvectors, which in this case here, eigenvector is going to be something we're going to talk a lot about. So the larger is the eigenvector, the more variability is in that PC. So each principal component is going to have an eigenvector for the different variables. And whenever we see here on this GIF, nothing happens for me when I run that chunk. Maybe, let's see, maybe make sure that you have the package knitter. I would imagine you would have. Is anyone having issues to show the GIF?
Yeah. Same.
It's not show, even if you load the package? So this is the package name. So
I do have the package for
it's still not running? Is it running for other people?
Yes.
Okay, so
It
Joseph,
run with the green, but we didn't see the GIF.
Huh.
But gives plan now.
okay, so what if you just copy this and paste in your browser? Maybe that would work. It's gonna, see, it didn't work. All right, so if you think about it here, you can clearly see that there is a positive relationship between these two variables, right? And PC1 is going to be, again, the first PC will always explain the most variability. PC1 here is starting at the origin and is on the direction of the largest variability, which is this direction along the relationship, right? So I guess this direction has the most variability. So that is PC1. PC2 then is going to be the next dimension of this relationship that has the most variability. So PC1 is always going to have the most variability. PC2 is going to be the second one after that. And then as you increase PCs, they explain less variability consecutively. And so on browser, it worked. All right, nice. Yeah, if it's not showing up here for some reason, you can just put that on our browser and it should work. But so just coming back here, we see that on this bivariate relationship that we're seeing, the largest source of, or largest direction of variability or largest dimension of variability is this. So that becomes our PC1. The length of this arrow is the eigenvector. So we can see it's a very long vector, so it has the most variability being explained by it. And then because we only have two variables here, we only get two principal components. Remember, it's one PC for each variable that you give the algorithm. So the largest direction of variability is this, that becomes your PC1. The second largest direction of variability after that is on that cross dimension. So that becomes your principal component number 2. So after it finds these dimensions of largest to lowest variability in your data set, then it rotates that in a way that you're not seeing anymore as like a positive relationship, but it basically rotates that in a way that gives you the coefficients rotated to make more sense for interpretability purposes. So this is basically what PCA is doing, but in our case, it's going to do that in 72 dimensions, which like after maybe 4 or 5 dimensions, our brains cannot really wrap that idea anymore. But that's basically the concept of what it's doing. Again, in this example, with only 2 dimensions, so it gives us back 2 PCs, which are the arrows that you see there, where the first arrow that has the largest length, the largest vector, eigenvector, is the one for PC1. The second arrow is the one for PC2. And you can clearly see in this example here that PC1 is explaining most of the variability of this data set, and PC2 is explaining the remaining variability of that. So this is the basic concept behind PCA. And of course, we're going to be doing a way more complicated data set with 72 dimensions. That is going to be even really hard for us to plot it and make sense. But that's the mathematical concept that's happening here. All right, so let's actually apply principal component analysis to our data sets and start looking into it, trying to make sense of it. So if you come to the next chunk, we're going to use this function called PRComp for principal components. We just give it the data set, so that is weather underscore n, which is the one that we only kept numerical variables. And then so this is an important point. We could, if we wanted, we could have scaled, normalized our variables already. But because PCA has the option of doing that for us, I wanted to not do that and show you how we can ask for PCA to do that for us behind the scenes. So we have this argument called scale dot. We can say true. So it's going to scale the variables for us before it runs PCA. If you set it to false, then it's not going to scale. And then 2 things can happen. If you set it to false and the algorithm does not scale for you, and you did not scale either, then you're allowing your variables with more magnitude in number to have a larger impact, which maybe is what you want, but I think most of the time is not what we want. If you set scale to false, the second option would be for you to scale on the wrangling step. So where we created weather n, we could have scaled that ourselves, which we're going to do when we get to the k-means. So we're going to see how to do that. But that's what we could have done as well. So since we did not scale weather n yet, I'm asking for the PCA algorithm to do that for us. So if we just run that, now we have this object here. I just printed. These are going to be some long prints, just because we have 72 variables and therefore components. So we have here standard deviation being explained by each one of the PCs. Perhaps this way of looking at it is not the easiest one, but you can really see that the standard deviation of the first PC is higher than the second, which is higher than the third, and so on. Keeps going down. So PC1 will always explain the most variability, have the largest standard deviation, and PC2 is going to be lower than that, and so on. We see here the rotation. So the rotation is just a matrix of the coefficients. So this is an interesting thing for us to look at. I don't think it's showing all of the variables here, but basically, so principal component is not a variable selection tool by itself by default. The reason for that is it's going to give you back principal components. So imagine you're going to have a formula where it's going to be principal component number 1 is going to be basically, imagine of a linear regression where we have all of our 72 variables and each one of them has a coefficient. Those coefficients are what we're seeing here. those are the eigenvectors of each variable for each one of the PCs. So really, again, you have 72 PCs, and each one of them is a different linear combination of all your original variables. So if you want to do PCA, you're still going to need to have all of those variables there to come up with the principal components. So it's not like you're going to say run PCA, and that's going to tell you these are the most important variables, and you keep going with that. It's not how it works. The PCs are still going to use all the variables to be derived. So you're not excluding or selecting variables here. You're just rearranging them differently in a way using different coefficients like we're seeing here for each one of the variables and each one of the PCs in a way that each PC is orthogonal. That's the main goal here, that they're orthogonal. And that in the end, because PC1, so let's say one of your variables here may explain, I don't know, 2% or maybe 3% of the variability of the whole data set. So each single variable is explaining a very little amount of variability. However, the PCs, which are combinations of those variables, will explain more than that, especially the first ones. So PC1 is going to explain a lot of variability, PC2 a little bit less, 3 a little bit less. There's going to be a threshold where below that threshold number of PCs, each PC is actually explaining less than your original variables, which we're going to see that in a plot in a second here. But again, with the goal being that we select a given number of PCs, maybe 1 through 5 or 1 through 2, 1 through 10, that are going to allow us to explain a certain amount of variability of the data set, but that number of PCs is less than what you would have needed if you only had your original variables. So we're going to see some plots I think are going to help to understand that, but that's kind of the concept here. If we ask for a summary, which we can do right on this chunk here, of mod PCA, I guess we see some of that output, but in a nicer way. So we have here importance of components. So we have PC 1, 2, 3, all the way down to 72, all the way to the end. And we have 3 rows if you think of that way. So the first one is called standard deviation. The second one is called proportion of variance. The third one is the cumulative proportion. So really, if we focus here on the proportion of variance, we see that for our data set, PC1 is explaining 35% of the total variance. So one PC is explaining 35%, PC2 is 26, and then see how it drops quickly to PC3. PC3 is only explaining 7% of our variability. And then this number here continues to go down, right? So PC1 will always be the highest, and it goes down from there. And if we look here on the cumulative proportion, so PC1 is again 35%. If we combine PC1 and PC2, we explain 61%. If we combine 1, 2, and 3, we get 69%, and so on. Right, so we see that maybe if we combine here 5 PCs, we're explaining 75% of the variability of this data set that actually has 72 variables, right? So we could use 5 instead of 72. Again, we still need all 72 to create the 5 PCs, but we can extract these PCs and run ANOVAs or anything, or like linear models of any sort, where instead of having mean temperature in July, I have PC1. And again, the other component is if you run a model where the PCs are your explanatory variables, they are orthogonal. They would never have multilinear issues, whereas your variables may have. All right, and so, I guess, if you start thinking here, when we get to 3 PCs, we explain about 70% of the variability. For me to be able to explain 100% of the variability of this data set, I have to use all PCs. So if you see here, we're only approaching 100%. I guess here's already rounding for us, but it would only explain 100% of the variability of this data set by using all 72 PCs, which then defeats the purpose, right? If you're using 72 PCs, I mean, you get the benefit of them being orthogonal, but as far as number of variables, you might as well use your 72 original variables. So there is a trade-off there of how much variability we're okay with explaining and okay with not explaining, making a selection of less PCs than we have original variables, and then using those for inference instead. All right, so then, a very good question is, how do you determine how many PCs you're going to use? This is gonna be possibly dependent on your analysis, on your objectives. But there is this tool here, which is a very popular plot that is called, it's called the scree plot, which we're gonna plot right here. So I want to tell you that some of these plots, or maybe most of these plots I'll be showing you, there is very manual ways of producing them. I will show you a function from a package that helps us to automate this visualization a little bit more. So one of them is called, the function that we want to do here is called fvis with a z underscore eig. So this function here is coming from the Facto Extra package, which is a great package for visualizing PCA results. So let's give it the model. So mod underscore PCA. We just run this. This is what it gives us. I do want to change one argument here that I wanted to show me how much of the percent of the variance has been explained. I wanted to show it on top. If you go on the documentation of this function, it has a whole bunch of things you can change for visualization purposes. I just want to change this one. So it's called add labels all together, all lowercase equals to true. So that's the code. This is the output. So this is just a visual way of seeing the same thing that we saw on that summary above, which is what is the proportion of variance on this data set that each one of the PCs is explaining. So again, dimensions here is the number of the PC number. So dimension 1 is PC1, 2 is PC2, and so on. And we can clearly see here that the largest gain in how much a PC explains is from PC1. That will always happen regardless of the data set. This is how the algorithm behind the scenes works. It looks for the dimension that explains the most variability, like we saw on that GIF, and sets that as PC1. And the next dimension, PC2. In our case, each one of the additional 72 dimensions will just breaking that down. So we see here, PC1 explained the most, PC2 a little bit less, PC3 a lot less, and then it kind of tapers off. We're really adding just one PC here is only increasing just under 2% of the variance of the whole data set, right? So there's a threshold here of how much we're okay with explaining and okay with not explaining, or we're making a decision of which PCs to keep. So one point to make here is that if you run PCA and you have this this behavior of PC1 being very high and then it tapers off after a certain point, it does mean that you have correlated variables, which is nothing new to us. But if you come to PCA and you give it, regardless of the number of the variables, but if they're not correlated, PC is not going to work well for you, because you're basically going to see that all the PCs are going to have a very similar weight, because really each one of them is almost explaining one of the variables if they're not correlated, right? In our case, we have many variables that are correlated, and that's why you see PC really shining here, because it really has this highest level of PC1 explained, and then decreases after that. Again, PCA works well when you do have correlated variables, and this is how it would normally look like when you have a scree plot, which is what this is. All right, so one of the ways that people determine how many PCs you want to keep with your further analysis is to determine the minimum level of the total variability in the data set that you want to explain. Right, so this could be, I mean, depending on the data set, this could be 50%, it could be 70%, it could be 90%, although 90% is probably going to require a lot of PCs to get there, as we saw on the table. But let's say if we were okay with saying, I'm okay explaining 70%, I don't need more than that, I'm okay with that trade-off. We can think of like, how many PCs we would need? I think there are different ways of looking and finding this answer. You probably, just by looking at the cumulative, you probably have already figured that out, right? So if we just come to this table here, how many PCs would we need if I want to explain at least 70% of the variability? 4, right? Because with 3, I'm explaining 69. If I want at least 70%, I need 4 PCs. And again, that 70% is just one example. You could go higher, you could go lower. As long as you report why you're doing that, it's normally okay. But let's say I want to show you here a slightly different way of looking at this. So let's make a plot that will require a little bit more coding from us. So let's start with mod PCA. I want to pipe that into a function that's called get underscore EIG for eigenvalue. So if you run this, we get the eigenvalue of each one of our PCs. So we have 72 PCs, we have 72 eigenvalues, which is related to that variability of how much each PC is explaining. And then I want to pipe that, or I want to pipe that into a mutate first. Because right now the PC number is in the row names. If you notice, there's no column title here, meaning this is row names. So I do want to create the PC number here, which I want to call PC, and that's just going to be a sequence of numbers from 1 to the number of rows of this data set. So that's how you would code that. And it's just like there's a new column now that goes from 1 to 72. I want to pipe that into a ggplot where I have on my AES at the ggplot level, I want to have my X to be equals to PC. So it's going to be that number. And then my Y to be equals to this variable here that if you want to copy, you can. If you want to type, you can as well. It's called cumulative.variance.percent. I want to add a plus and want to add a geom bar. So I'm going to have a bar for each one, a vertical bar for each one of the PCs, showing me what level of cumulative variance they explain. You need to say stats equal identity for this to work properly. So if we just run that, this is what we would get. Is very similar information to before. We're just looking at a different way, right? So we have our PCs on the x-axis, and then the cumulative variance as a percent of the total that each additional PC is explaining to you. And so let's say if I wanted to just visually add here a line at 70%, so I could visualize that, we can just come back to the code, add a plus, and do a geom age line for horizontal line, where it has this argument for y-intercept, and I can say y-intercept equals to 70, because that's the number that we decided. So this, again, is another way of seeing that you would need 1, 2, 3, 4 PCs. I guess a more visual way of determining the number of PCs. But also another way for us to see that tapering off of the PCs, right? So and this again is the cumulative. So that's why this plot is looking, it tapers on the top, whereas the previous one tapered on the bottom. The previous one was not cumulative, right? So the scree plot was not cumulative. So each individual PC explaining this much tapers off at the bottom. This here is cumulative. So each additional PC, how much that's adding to what the previous ones were explaining, that's why it tapers off on top. So we can see that we would need, again, 4 PCs to explain at least 70% of our variability.
Can see the previous code?
Yeah. All right. So as I was telling you, principal components, you get the same number of PCs as you have variables. So we have 72 principal components. Each one of the 72 principal components involve all the variables that we gave it in different ways. So it combines them in different ways. And the way that it combines them differently is by assigning a different loading or a different coefficient to each one of the variables. So again, imagine a formula where you have PC1 equals to, and then each one of the variables that we gave, so 72 variables, and where each one of those variables is multiplied by a coefficient. this coefficient means how important is that variable to that PC? And only to that PC, because that variable may be very, so let's say mean temperature in July may be very important for PC1, so it may have a very high loading value, but it may be unimportant to PC2, 3, 4, 5, and so on. So it's going to have a very low loading value for other PCs. Depending on the problem, depending how many variables you have, you could also use the loading values for each one of the variables for each one of the PCs to try to create interpretations of what a PC means. So let's say you would look into PC1, look at all the loading values, especially the very high or very low ones, and try to give it some interpretation, which is what we're going to try to do here in the next slide or in the next chunk. So let's look into principal component number 1 and look into the loadings, so the weights that all these variables have in PC1. I left you the code there already. So I'm taking the mod PCA $ rotation, which is the rotated loadings from the PC, turning that into a data frame. I guess, Joseph, you were asking, so if you look mod PCA rotation is, I think is this. It's not a data frame, it's maybe an array. I'm not sure what's the class of this. I'm plugging that into an as data frame to force this to be seen as a data frame, because then I can, using ggplot. And so it has the row names here, which is not a column, or row names only. So I'm using the function row names to column to force those row names to then become a column that I can call in ggplot. So now they become a column. And then I'm plugging that into ggplot, where I am reordering all the PC numbers on the x-axis according to the height, from the highest to the lowest. I'm leaving you the code there. I'm adding the geom bars, and I'm having the fill of the bars on a gradient from low to high, where low is red, high is blue, and then just changing the theme a little bit. If you do want to explore this code on your own, you can always come here if you want to know what each part of the code is doing. You can just come here, add a hashtag before a plus, just run until there, see what happens, and then let it go through the next one, run, see what happens, and so on. This is what I do when I'm troubleshooting code a lot as well, especially this connected codes with pluses and pipes. So if you just run the whole thing, this is what you're going to see. So again, for PC1, we have all 72 variables as part of it. Just like for every other PC, we have all variables as part of each one of them. So here we're inspecting PC1, and the loading or the eigenvector or the weight, I guess would be synonyms of the same thing, of different variables towards PC1. I'm going to try to increase this so we can try to read which ones are really impacting it. So the way that I would interpret this, so you see here, mean day length in January, mean day length in December, February, November are all the top 4 here. So they're all here. Then we have some others that do have some weight, but the importance of them starts to decrease towards PC1. There is a group of variables that have very little influence on PC1. And then we have, again, on the flip side of that, some variables that have a very high negative importance on PC1, which, interestingly enough, are also mean day length variables, but in this case, July, June, and August, April, I think. So if we, I guess, let me ask you all this. If we had to interpret, before I ask you this, let me give you a little more background. So whenever we see these variables in any PC, you have different variables impacting. Some are going to be more important, some going to be less important towards that PC. And if they have different directions, in this case, we see here, these have a positive direction, these have a negative direction because it's centered on 0. It means that they're almost like inversely related towards that PC, right? So really, I want to give you just a quick moment to think about it, even though it may be a little bit difficult, but mean day length in January, December, February, November, and October are on the top most important on the positive side for PC1. And then on the bottom most important ones on the negative side, we have the same variable as far as day length, but in different months. So one thing people would try to do if possible is to give these PCs some interpretation. Sometimes it may be difficult, it may not make sense. But here, I guess, in this case, we kind of, can come up perhaps with some interpretation for what PC1 is really meaning to us. It's really telling us about this data. Anyone has any thoughts? I guess there's no right or wrong answer. It's just, trying to interpret what we're seeing here. Like if you had to write down on a paper the way that you would interpret this principal component based on these loadings for the different variables, what would you say? So I guess, what I would perhaps at least try to begin from that perspective is just realizing that the variables that have the highest influence are all mean day length related, right? Pramod, you have a thought?
The 4 bars on the right end and the 4 bars on the left are kind of the same size.
Mhm.
So they're getting equal weighting.
Right.
Is that,
So it doesn't necessarily cancel out, it's just telling you that they're inversely related towards that PC.
but in equal weight?
In equal weight, yeah, exactly. Yeah, so I guess where I would start here is perhaps at least for PC1, we're seeing that the variables both on the positive and the negative side that have the highest loadings are all related to mean day length, right? So definitely PC1 is telling us something about mean day length. When it comes down to all these variables, mean day length is what is most important for this PC. And if you look at it, if you try to understand the structure of what we're seeing on this plot, the mean day length on January, December, November, October, and March are on this side of the equation, are on the upper side, I guess, of the 0, and mean day length of July, June, May, April, August are on the other side. So maybe PC1 is telling us something about the mean day length first, because both sides, mean day length is the only variable that is predominant, and then maybe in different seasons, right? Because we see that months that are colder are all on the left side here. So January, December, November, October, March, and the months that are hotter, warmer are all on the lower side of it. So, it doesn't always happen like this, that you can come up with an interpretation. In our case, I think, we can try to come up with something that is related to mean day length in different seasons, right? In different, especially really cold, really hot months. So that would be a way that we could interpret this to some extent. Any questions? All right. So I'm gonna keep moving here. If we come to the next chunk, let me get to my code here. So we're gonna use a function that's gonna help us to visualize this in a different way. So the function name is fvis underscore contrib or contribution. So we give the mod underscore PCA. I want to change a couple of arguments here. So one of them is called choice. I want to say choice equals to var. And the next one is I want to change the argument axis to be equals to 1. So this is just to make it look a little bit nicer for us to interpret. If you want to understand better why I'm making these changes here, you can always go in documentation of this function and read more about it. So this would be a similar, a different way of looking at this, but it's still a similar interpretation where we have the contribution as a percentage of each one of those variables towards PC1. And remember that we're just talking about PC1, right? We're not talking about any of the other PCs at this point, just PC1. So we see here the contribution of different variables towards PC1. And the dotted red line here is just the overall average contribution across all variables. So the way that we could interpret this is anything that it has a larger contribution than the average would have an important weight. I mean, in this case here, I don't know how many variables it would be if we consider that, probably, I don't know, 15 or around that. Which, starts to adding more complexity to interpret. But we could use this as well to understand. So we see here that when you remove, or when you put this in a percent contribution, rather than just using the eigenvector or the weight of each one of the variables. So here we're looking at the weight. Here we're looking at contribution. So a different metric, but it still tells us the same information. So we see here mean day length, July, December, I think it's January, February. So all of these first variables here are all mean day length, as what we saw before, right? It's just that now they're all going in the same direction for us to understand. So this would be another way that you could look into this and understand what variables are impacting PC1. And again, this is just for PC1, which is normally the one that you'd be most interested in because it is the one that explains the most variability. In our case, we may also want to look into PC2, 3, and 4, perhaps, but I'm showing you here for PC1.
So what happened to the negative ones?
So what this function does is behind the scenes, it just calculates the contribution. I don't know exactly how it calculates that. It may just be how much of the variability from that variable is explaining towards that PC in some way. And I don't quite remember how this algorithm calculates that. Whereas here is the actual eigenvector. So this would be the coefficient, right? The coefficient here for PC1 of mean day length in January would be like 0.17, I think it was. Right, so that's what we're seeing. Here's the actual coefficient. If you think of PC1 equals to all the variables and each one of them multiplied by a coefficient, that's what we're seeing here. And in contribution, this is not the coefficient. This is just how much variability that variable is contributing towards that PC. So I'm not sure how it calculates behind the scenes, but they're different metrics, right? Okay, so I want to check now the eigenvectors for both PCs 1 and 2. So I left you, I guess, everything here. And I do want to run it first. So we're using this function fvis PCA var, given the PCA model object. I'm asking for contribution to be the color that is given to each one of the vectors, is given as a gradient of colors that I specify here. And I'm asking it to add the labels and repel them. So we see the directions of each one of the variables towards both PCs. I want to run this first and tell you that this is very difficult to understand because there are 72 variables, so there are 72 arrows with labels, which is nearly impossible to understand. However, if you ever read a paper that included PCA, this is a very typical plot to show, where you have your dimension 1, which is PC1, and how much variance that PC explains. Have your dimension 2 on the y-axis with how much variance that explains. And then you have this, this is also called a biplot, where, so imagine that here PC1, so if you look at the x-axis only, right? PC1 is centered on 0, goes negative, goes positive, which is what we were seeing here on these variables only for PC1. But then it also adds PC2 on the y-axis, and it sees how things are, how they land on this plot when you consider both PC1 and 2 in each one of the axes. And in this case here is giving us the vector here is basically the eigenvector we're seeing are these coefficients here. The larger is this numerical coefficient, the longer is the arrow. But now we are looking at that intersection of how important a variable is to both PCs, right? So let's say if we had variables that are very important for both PCs, they may, let's see, let's think about it here. So they may go on a diagonal direction and be very long, right? So let's say if something would have a very high loading, positive loading on both PC1 and 2, it would go this direction, right? It would have a 1 on the y-axis, a 1 on the x-axis. So it would be a diagonal and very long. Whereas if it is not as important, it's gonna be shorter, right? So it's not gonna extend as much. So anything that's shorter here is not as important to both of those species. And I do want to show you here another argument we can change just to make this a little bit easier to visualize. So if you come right after that true, you add a comma, and you can go at the end of that comment and break code just to allow that comment to remain with that line. And there is an argument called select var that I want to ask it to only show me a certain, so only variables that have a given contribution. The way we do that is we call a list and we say contrib, and I want to say contrib equals to 5. So it's going to only show us variables that have a contribution equals to 5, and not all of them. So if you run that, it will only show, again, those variables for us. So we see here that on this contribution scale, if we just look at PC1, so imagine like we were looking earlier at PC1, right? So if you just look at PC1, mean day length in July is going that direction. So only on the X direction, if we think about it, day length in July is going that way, and then day length in January and February are going on the other direction. Here, the same as vapor pressure in January, vapor pressure in May are also going into the positive direction here, which is kind of interesting because now this is the contribution across both PCs, not just PC1, right? So it's the combined one. So if we were to do these plots for PC2, I bet that VPA in January, that vapor pressure in June and vapor pressure in May would be very important for PC2 because they're appearing here on the combined importance for both of them. So this is just an easier way for us to not have all those variables overwhelming us here in the labels, but at least some of them so we can see make more sense. But again, this plot is a very popular plot if you're doing PCA. You probably have seen this in papers if you ran across those types of papers. And I guess on this plot here as well, the same interpretations we had before. So if they are perfectly opposite in the same angle for different PCs, it means that they would have a inverse effect or inversely related effect towards that PC. So we see here mean day length in July being opposite to mean day length in January and February for PC1, which is what we already saw on that first plot. So these things are inversely related as they impact PC1. And they also have some importance in PC2 because they also appear here. But then PC2 is bringing us vapor pressure in June and May going in the same direction. So they are correlated in the same direction with PC2. All right, so one way of showing this plot is what we just did above. Yes, you have a question?
Can we go for the code? Sure. Okay, thank you.
Mhm. So one way of showing PCA data is to show the eigenvectors as we just did. So having PC1, PC2, and having all these arrows in different directions. And again, the longer is the arrow, the more important that variable is towards that PC. The other way to show this is to show the PC scores. So I wanna first make this plot and then tell you what do I mean by PC scores. So let's make a similar plot as before, but showing the scores. So we're gonna call this function fvis underscore PCA underscore int for individual. We're gonna give mod underscore PCA, so our model, and has one argument I want to change that is called label. I want to say label equals to false. So this is also called a biplot where we have PC1 on the x-axis, PC2 on the y-axis, but instead of showing the direction of the vectors of the variables, it is just making it's using the model that it created to make a prediction of where each one of the 678 points would fall if you were to give the value. So because again, if you think about it, let me just take one step back here and think about it again. Think of the formula PCA1 equals to all these variables with each one of them having a coefficient. Now you go to one of those side years and you replace the variable with the actual value of that variable for each one of these. You get a prediction of PC1 for that side year. That is a PC score. That's what we're seeing here. Okay, so let's just go through that again. Imagine if for each PC, we have a formula PC equals to all the variables, and each one of the variables are multiplied by the weight or the coefficient that we already saw. And now I want to know a prediction of where would each one of these side years fall if I use that formula. So instead of having variable name times a coefficient, you have the actual value of that variable for that side year times that coefficient, and this is all added together. So it's mean day length in June times the coefficient plus mean day length in July times the coefficient, and so on for all these variables. So now we're asking for a prediction for each one of our side years, and that is called a PC score. That's what we're seeing here for each one of our variables. I'm sorry, for each one of our observations for both PC1 and PC2. So if we look into this, if we just think about the visual aspect of it, it kind of seems like we have some groupings, right? Even though some people use principal component for cluster analysis, I don't really know. I mean, I feel like there are better algorithms for clustering. I prefer to use PCA for dimensional line reduction, orthogonal PCs, so no multilinear problems, but not really for clustering, even though some people do. So if we were to use this for clustering, we can kind of see, some groupings. So this is by itself here. Maybe these each would be a cluster. I mean, I don't know, maybe this would be a cluster, this, that. I guess it depends, right? But we can just see here how there may be some groupings that we're getting from PC and just using two PCs, right? So imagine it would be only two variables in the model. Okay, so just recapping here. So we learned that all the way from the beginning of the exercise, we have some original variables that are strongly correlated, that we needed at least 4 PCs to cover at least 70% of the variability of the original variables. The most important variables in PC1 were related to day length in winter and summer months, and the opposite direction. And what I want to show you here before we move to k-means, which I think is probably where we'll end for today as we're getting close to the 11:10, is I want to extract the PC scores for the first 4 PCs, and I want to try some models with that. So we can actually test if we run 4 PCs in a linear model, are they going to be multicollinear or not? They should not be, because that's how they were developed, but I do want to show you and check that with you. So what we're going to do here in the next chunk is just to extract the PC scores so PC score is, again, something you do at the observation level, and you get it for as many PCs as you wish. I want to get for the first 4, but there are PC scores for all observations for all PCs that we have. So if you come here on this chunk, let's call our mod_PCA model object. If you use $, it has this X data frame. If I just print that, this is the scores for each one of our observations. It is not a data frame. It is like a matrix, I guess, format, or maybe an array. I want to transform that to data frame. So let's give it a pipe and call as.data.frame. If we just print that, you have 698 rows, because again, remember, each site year in our data set has a PC score for each one of the principal components. So PC1 here is the first column. This is the PC score for each one of those site years. And then we have 72 columns where each one of them are a different PC with a prediction of what would be the score for each one of the site years. Because I only want to keep PCs 1 and 4, let's just do a pipe dplyr : select. I just want to do PC1 : PC4, where PC is uppercase. So we end up with 698 rows still, but only 4 columns, which are PCs 1 through 4. All right. Next step here is I want to add those 4 PCs that we just created as columns of our original weather data. I want to just bring them together and bind those columns. So if you come to the next chunk, that's what we're going to do here. Let's give it the assignment symbol. I want to start with weather. Oops, just weather. So if I just print weather for you to see, that is our original data set with 698 rows, 75 features. So I want to come here to a pipe, and there's a function called bind_cols for columns. So I want to bind the columns from the object, excuse me, that we created above, which is called PCA_scores. So if we do that, we should still have the same number of rows, 698, but we have 4 extra columns in the end. I'm not going to go all the way there, but there are 4 extra columns in the end that are for the PCs 1 through 4. All right, so now let's run a linear model trying to explain cotton fiber strength, but instead of using our original variables, I will use the PC scores from 1 through 4. So if you come here, let's use LM, a very simple linear model, where the Y variable is strength in G text tilde. And then here, imagine that if we had not run PCs, we would have our original variables here, right? Because we ran PCA, we extracted the scores of the first 4 PCs. That's what I want to use here. So we just say PC1 plus PC2 plus PC3 plus PC4. And then we need to give it a data set. So data equals to weather post PCA. So if we run that model and then get a summary of it very quickly, I mean, it's just the regular summary that we get from linear models, but we do get an estimate of how strength is changing according to PCs. Right, and then what we can see here is that at least for this case, explaining strength with 4 PCs, we see that PC2 and PC3 have a significant effect on strength, whereas PC1 and PC2 do not. All right, so the next thing here is I want to check the variance inflation factor of this model, which our hypothesis coming in is that the variance inflation factor would be 1, because these PCs are orthogonal, are independent, are not correlated. So if we use the VIF function on the model object, that is called LM_PCA. Notice how the variance inflation factor for all the 4 variables are 1. That's what we would expect, right? Now imagine if instead of using PCs, if you had used, I don't know, 4 different variables, especially if they were correlated, your VIF would be probably higher than 1, probably higher than 5, meaning multicollinearity issues. So again, we could have included here all 72 PCs. They would all have a VIF of 1, because that's how they are mathematically derived. They are orthogonal, they are independent. All right, so I want to make one plot here, which is I want to plot, kind of show a scatter plot of PC1 versus strength to really visually assess that relationship is not very strong. So let's call ggplot here. We're going to call our weather post PCA data frame here. On the AES, so if we just print this very quickly, weather post PCA has all those variables, but on the X variable, I want to have PC1. Remember, there's a column called PC1. On the Y axis, I want to have strength. So strength underscore GTEX. If you get all the way outside of the ggplot, let's add a plus and get a geom underscore point. We can just run that. And we can, I mean, already visually see that there's really not like no relationship here. We could further explore that by adding a geom smooth, where we change the method to be equals to LM, as this was the model that we were running on the LM above, this linear model, right? So we see that, you know, there's really no relationship here. So even though PC1 is increasing from -10 to 10, we see that strength in GTEx is constant around 30. So no relationship here, as we would expect from this summary, that we saw PC1 at a very highly non-significant p-value towards strength. Now let's do the same thing for PC2. I already left through the code as we just developed that already. Just now we're plotting against PC2. We see that there is a positive relationship here, even though still quite noisy, right? But we see that there is a relationship, so the slope here is significant, which is what we would expect based on the linear model summary that we ran above, where PC2 and 3 were significant. Doing the same thing for PC3, which was also significant. So notice how this is interesting, because PC2 was related with strength in a positive way, right? As we saw from the summary, but also from the plot here. So as PC2 increases, strength increases as well. And PC3 is on a negative relationship with strength. So a different type of relationship than PC2. All right, so as we already knew from that linear model summary, only PC2 and 3 explain strength. And then again, if you were doing this type of analysis and you would like to give some interpretation, you will go back to PC1, go back to PC2, look at which variables had the highest loadings or weights on those PCs, try to come up with some interpretation of them, and then say, you know, in this case here, we would say, well, the difference in mean day length from summer to winter did not affect strength. That's our interpretation of PC1, and we saw PC1 had no effect on strength. That's how I would interpret this. But then, of course, we did not look into PCs 2 and 3, but we could do that very easily by using the similar functions. Okay, so we wrapped up PCA. Any questions about PCA itself?
No. PC reduce the problem of multicollinearity by reducing the weightage given for those variables that has correlations.
Yeah, so basically, yeah, so Benita's question is if PC fixed multicollinearity, but given different weights to different variables that were correlated. That's a good summary of it. So again, each PC is going to be a different linear combination of all the original variables. So each PC still has all the original variables, but the weights that each variable has in each PC is going to be different. And the way that determines those weights is based on this correlation between the variables, right? So I guess another way to think of it is if you give PCA 4 variables that are completely uncorrelated, they have nothing to do with each other, and you give 4 variables, and PC is going to give you back 4 PCs because same number of PCs as variables that you give the algorithm. If you give 4 completely uncorrelated variables, it's basically going to give you back each PC having a very high coefficient for one variable and very low coefficient for others. And then the next PC is going to have a very high coefficient for a different variable and very low for the others. In a way that is almost like each PC is only being affected by one of the variables, right? Because none of them are correlated. In our case, we have many correlations of different levels on this data set. So each PC is almost like grouping those variables are correlated and giving them different weights to account for that correlation for that PC. And once that is explained and out of the question, then it goes to the other dimension, the other PC, and sees how much correlation is left. And now let's give weights to these variables that we explain the next level of correlation in PC2. Once that's out of the way, it goes to the next one, and so on. Any other questions? All right, so I guess next class, we're gonna do K-means. I don't think K-means is gonna take the whole 2 hours. So what I would say is make sure you do not miss next class because I'm thinking of having an in-class. So maybe the first hour we use for K-means. And then the second hour, I'm gonna do an in-class assignment for you to have some opportunity to make up some of the grade that you may have missed on the midterm. So do make sure to come. I'm not sure yet how that's gonna be. I'm gonna plan that in the next couple of days. All I'll tell you is make sure you're in class, because that's gonna be an in-class only exercise that you're gonna have some chance to, or gonna have a chance to make up for some of the grade that you may have missed on the midterm. So let me get your attendance. Yeah, so I was given an extension to some students and I decided to make this across the board. So if you're ready to submit and you want to have that out of your plate, feel free to submit by this Thursday. But if you do need more time to complete your assignment, then we're gonna have until next Thursday as deadline. All right, I guess that's all I had from my side. If no one has questions, then we'll wrap up and I'll see you on Thursday.